All right. Good afternoon, everyone. Welcome to the third student seminar in the Maryland Robotics Dinner Student Seminar Series for spring. Today we have Rohan Chandra, who is going to give us his presentation on a paper that was published recently where you would model human behavior, that robots would model human behavior. So without further ado, I'll hand it over to Rohan.
Right. Thank you, Lena. So hi, everyone. My name is Rohan Chandra, and today I'll be talking about modeling human driver behavior in dense urban traffic using graph theory. So before we get into the meat of the talk, a little bit about myself. I'm a third-year PhD student working with Dinesh Manocha in the computer science department at UMD. And my research goal in my PhD is to advance autonomous driving in dense and urban traffic where drivers may or may not always follow the traffic rules. Now, the structure of my talk is roughly structured as follows. I'll begin by motivating the problem statement and followed by formally describing the statement. I'll discuss very briefly some of the prior work that has gone into solving this problem, followed by the details of my main algorithm or approach. And finally, I'll talk about some of my results and direction for future work. So I'll begin by the motivation. So our work is motivated by applications in autonomous driving. And as we all know, currently there's been a lot of progress in terms of computer vision, robotics, and controls in autonomous driving. And you've probably heard about progress in detection, prediction, as well as planning. But what has not been addressed so far is the notion of social awareness in autonomous driving. And this is sort of a fuzzy notion, social awareness. And in the next couple of slides, I'll show you two videos or two video clips of the Tesla autopilot in the real world traffic scenarios, where hopefully this notion of social awareness will become more clear of what it is and why we need it. So I'll play both videos first, and then I'll go into the explanations of each video. And let me know if there's any problem with the audio, you need me to increase or decrease the volume, and I can happily do that. So let me play the first video first. All right. So this was the first video, which showed a Tesla trying to lane change. One sec. Okay. All right. Well, essentially what happened in the video was the Tesla autopilot was trying to change lanes in the traffic, but it got honked at because the Tesla autopilot was very, very cautious and very slow in trying to attempt a lane change. And so the driver was just pointing that out, that the lane change was very, very cautious and slow and not at all how a human would switch lanes. Okay, so in the next video, I'm going to try, let me increase the volume for the next video. Right. Let me know if this video, the volume plays well. Okay, not sure if the audio was good on this one, but essentially what was happening, All right, let me try closed caption. Oh, I don't think I have closed caption on this. Let me just summarize what happened in these two videos. So in the first video, what happened was that, yeah. So what happened in the first video was that the Tesla autopilot was trying to switch lanes in very dense traffic, but it was waiting for a very larger than necessary gap before it would switch lanes to the target lane. So what ended up happening was that it blocked a lot of the traffic behind the Tesla. In the second video, it was attempting to maneuver in trying to navigate through a very busy intersection, wanted to turn right, but normally how you turn right, you sort of creep up towards the corner and then wait for all the pedestrians to cross. But the Tesla simply stood still and waited for all the traffic to clear before it attempted to even go up to the intersection. And this sort of caused the driver behind the Tesla to honk in irritation and frustration. So this is what is meant by social awareness, where you don't drive cautiously all the time, but in certain instances, you want a certain aggression, or the word is confidence. You want to be a little confident in such kinds of traffic scenarios. And if you don't do this, if you're acting cautiously all the time, which is by default the natural design of current autonomous vehicles in the interest of safety, what ends up happening is that you cause the human drivers around you to become frustrated or irritated. So a counter question to this is that why do we care about this? Because these kinds of instances are far in between and very rarely occurring in the real life, right? But then I will say that, yes, that is true, that in developed nations like the USA or Europe, uh, these instances are not very common, which is why we have autonomous vehicles on the road. But what about places like developing nations like India or China, right? Where drivers routinely break rules and the traffic and the driving is exceedingly complex. So in these kinds of traffic scenarios where you don't have lane driving, you see pedestrians crossing the roads at random weird moments, or when vehicles drive on the opposite side of the road. Now, here, where the driving is not dictated by rules, it is very crucial to try and predict the behavior of the agents around you. And this, speaking from a personal perspective, this is how drivers in India drive on a daily basis, by trying to intuitively infer or guess the behavior of the drivers around you, try to predict if they are aggressive or conservative, and then try to model or perform actions based on this. The social awareness is essentially in dense traffic is trying to perform behaviorally guided actions based on the behaviors of the drivers around you. Okay, and that leads me to my problem statement, which is at a very high level, given the trajectory of a vehicle, I want to predict the behavior or the aggressiveness of the driver. Now, why I've underlined this part is because in a couple of slides, I want to replace this high-level definition or high-level statement with a more low-level, computationally tractable problem statement. But for that, I need to have a model of driver behavior or what it means to model driver behavior, because driver behavior it's in itself is a very subjective notion. So what is the driver behavior model? So from past studies or prior studies in traffic psychology, driver behavior is essentially a global behavior label, which could be aggressive or conservative. And each global behavior is made up of a combination of specific styles or indicators. So I'll take one example. Let's say we have a very aggressive driver. That aggressive driver is going to perform certain maneuvers like overspeeding or overtaking and such. On the other hand, a conservative driver would typically have a uniform speed, may underspeed, or conform to a single lane. Now, why this is attractive for us is that instead of having to model uh, subjective notions of global behavior, which is aggressive or conservative, we can instead focus on modeling the indicators, which is much more computationally tractable because these indicators are essentially functions of trajectories. So we can model overspeeding, we can model overtaking based on the trajectories of the vehicles. So this sort of underlying notion of a classification-based system of global and specific styles gives us a way to model the global behaviors via the indicators using the trajectories of the vehicle. So now we are ready to state the uh, computational aspect of the problem statement, which is given the trajectory of a vehicle, I want to model the specific styles, which could be the overspeeding or overtaking, to predict the global behavior label of a vehicle. Okay. And now, uh, before I go into the discuss the prior work, I'm happy to take any questions if there are. Feel free to raise questions in the chat or unmute and ask me questions. Okay, so I won't go into a lot of the prior work because that's not the focus of this talk. But broadly, prior work has taken two main kinds of approaches. The first approach is that prior work is based on studies in traffic psychology, which has mostly been in the form of questionnaires. So this is done offline, where drivers are asked to come in and answer a bunch of questions on a list of set of questions, and based on the responses of those questions, the driver's behavior is determined. So those questions could be, do you normally leave a lot of gap between vehicles? Do you brake often? Or behavioral psychological questions like that. So these are mostly research which is done in traffic psychology. On the other hand, there are data-driven models which I purposefully have kept it very broad and vague because a lot of methods are classified as data-driven. So what these set of methods do is that they collect a bunch of trajectory data, and then they perform statistical techniques to try and infer a set of features or behavior features to try and uh, to detect or infer the behavior of the driver. The main disadvantage of data-driven models is that these models only work on the data that they have been trained on. And so, for example, if you train a data-driven model on Washington, D.C. traffic, then it's a very strong likelihood that it's not going to work for New York traffic. And so the main problem that still arises is that predicting the behavior of other human drivers in real time in any traffic scenario remains an open problem. And that is precisely the kind of the problem that we want to tackle. So I come to my solution now. We use a notion called vertex centrality. So what is vertex centrality? Vertex centrality is a concept in graph theory that models the relative behavior between vertices. The centrality measure of a vertex is a real valued function that describes the importance of a vertex with respect to its connected neighbors. So I'm going to go into a bit of detail about this in a couple of slides. But first, why do we need relative behavior? And that is the workhorse of my approach and why my approach actually works. So relative behavior is important for a number of reasons. Let's take a few examples. First, suppose a vehicle drives at around 65 miles per hour. Now, the task is to predict whether that driver is aggressive or conservative. But this raises certain questions. If you're driving at 65 miles per hour, you could be aggressive in a city, but you could be neutral on a highway, right? So you need some context. An example two, a vehicle changes lanes, let's say 3 times per minute. Is it aggressive or conservative? It could be aggressive for a truck because of the slow maneuverability of a truck, but maybe not for a car. But then wait, is 3 lane changes a minute high or low? And you can see that it also depends on traffic density. So there comes the importance or the requirement of relative behavior, because humans observe driver behavior relative to themselves. They don't know what is 65. They don't even know that the vehicle in front of them is moving at 65 miles per hour. They just know that the vehicle in front of them is moving faster than them. And that is how they decide that the driver in front of him is aggressive. So this is the notion that is captured by vertex centrality. And vertex centrality is not something unique. It has been used in many different types of applications. It's been And some of these applications are very well known. For example, Google search engine, the PageRank algorithm uses vertex centrality. The main algorithm to rank chess players, that also uses centrality. And then centrality has also been used to determine the origin and the destinations of pandemic points, also to analyze different computer servers on an IT. And now we, in our approach, in our paper, we propose the first use of vertex centrality to model driver behavior. So there are many types of vertex centrality functions. The two main ones that we use in our approach is the degree and the closeness centrality. The degree centrality measures the number of edge connections to a vertex. So you just measure the number of edges that go in or out of a single vertex. And the closeness centrality measures how central the vertex is in a graph. This is essentially modeled by measuring the distance from a vertex from all other vertices. So I won't go into the mathematical portion of it. I'll refer you to the paper for that. But at a very high level, on a broad level, the degree centrality is used to model longitudinal indicators, which is along the axis of the road, such as overspeeding. And the closeness centrality is used to model the lateral indicators, such as overtaking, sudden lane changes, or weaving. So maneuvers which are perpendicular to the axis of the road. And we use these two vertex centralities. We first use them to model the specific styles, such as these maneuvers. And from these maneuvers, we then classify the overall behavior, such as aggressive or conservative. So now I'm going to demo an example in which I use the closeness centrality, and I show you how it can be used to model a lane changing vehicle. These graphs have been generated using Python, using the NetworkX library. And on the left, I'm showing a traffic network at an initial time step. And the graph on the right shows the same traffic network that has moved after a couple of seconds. And we're going to focus on the ego agent that is marked 1 and in color red. And as you can see at the beginning of the traffic, it is perhaps at the bottom of the traffic towards the side, but after a couple of seconds, it moves to the center. So this is supposed to model a lane changing, or it could also be an overtaking or a zigzagging vehicle. But the main point to note is that it's a lateral maneuver or lateral specific style. So from the bottom, it moves towards the center. So we can now use the closeness centrality. We apply the closeness centrality formula, and we note the distances of the red agent with all its green neighbors in the first instance, where it's towards the bottom, and all the green neighbors are sort of at a certain distance to the red. But after the 2 seconds that have passed, the red vehicle has moved towards the center, maybe trying to simulate a lane change, and the distance of the red agent with all the green neighbors has sort of shrunk. So this is captured by the closeness centrality. And in the first case, we measured and it comes out to be 0.44. But in the second case, it increases and it measures out to be 0.72. Now, what we do with these numbers is that we can plot it on a graph. And we do this for during a time period. We do it for every time step during the time period. And we can use the regression to plot a curve, to fit a curve to predict the centrality in the future. So this at a very broad level, in a very nutshell, is sort of how we use centrality to model the indicators like maneuvers, and we use this to describe our approach. Now, as the input, we read the coordinates of every vehicle at every time frame, and then we form traffic graphs. So the traffic graphs are formed by using the coordinates of the vehicle as the vertices, and the intervehicular distances form the edge costs. And then we can use the vertex centrality functions to compute the vertex centralities and plot the graphs. So now I'll show you some of the major results of our method, and then I'll talk about some of the future work directions. So I'll play a video. There's no volume this time. And I'm going to pause a little bit in between and describe what is happening and how we're actually modeling the behavior. Yeah. Okay, so the first example is trying to model an overspeeding vehicle. The ego agent is marked in green, and all the neighboring vehicles are marked in blue. The graph on the top right shows the degree centrality versus the time step or the frame number. Now, the whole point or how the modeling goes is that the degree centrality, it measures the number of new vehicles that the green agent observes. And the whole idea at a very broad level is that as the green agent overspeeds, the degree centrality should increase, as opposed to the blue vehicles, which remains flat. So as the green vehicle is overspeeding and it's observing new blue vehicles as it goes along, the degree centrality keeps increasing. All right, so the second example I'm going to show is of a lane changing vehicle in simulation. So again, the semantics are the same. The green vehicle is the ego agent, while the blue vehicles are the surrounding vehicles. And here the idea is that as the ego agent moves from the center towards the side, the closeness centrality decreases, and vice versa. As it moves towards the center, the closeness centrality should increase. So as you could see, as it moved towards the side, you saw the closeness centrality decreasing. And we also performed some real world experiments where we use real world trajectories to model various behaviors. The main advantages of our approach is that it is robust to noise and perception. And we actually have a theoretical result in the paper that shows this. And it is generalizable to many traffic environments with minimal to no assumptions and restrictions, except for the fact that you need the trajectories in a global coordinate frame. So these are the two main advantages that actually enable our method to be used online and with no restrictions to the kind of data that you need to run the model on. For future work, there are a few limitations of our approach. And one of the more major ones is that our work is currently limited to only modeling the behavior of the drivers. But what we can do is you can use that driver behavior to perform planning and navigation. So that is something that we're looking to do, and we're trying to integrate our driver behavior modeling with some global or local navigation planners, and try to create an end-to-end navigation algorithm using behavior-driven model. Another interesting possibility is for risk estimation, where you try to directly use the aggressiveness information of a driver to assess how much risk he possesses or affects on the drivers around him. And this can be used for safety control, safety enhancing measures for current autonomous vehicles that are already deployed on the road. So in conclusion, I first discussed what social awareness is in autonomous driving, why it is important, and how it can be achieved by inferring the behaviors of human drivers. I presented an approach for modeling driver behavior in dense traffic based on the idea of vertex centrality. I claim that my approach is robust to noise and generalizes to different traffic scenarios. And I also showed some results in simulation and real world traffic scenarios. And this is the end of my talk. And you can always reach me at this email ID, or if you want more information about the paper, you can visit the project webpage. So I will stop now, and I'm ready to take any questions if there are.
Thank you, Rohan. For anyone who has questions, please put them in either the chat or the question and answer box. We'll just wait for a little bit.
Okay, so I see a question. How does this approach handle pedestrians or and handle the unexpected behavior of pedestrians? That's actually a very interesting question, and I did explore this as a side project. Um, so the short answer is I've used this approach to model the behavior of pedestrians separately uh, as a standalone pedestrian model. So it works. So this idea of vertex centrality works within a pedestrian only scenario. I haven't had the opportunity to test it in mixed traffic where vehicles and pedestrians exist. Uh, However, it works in a mobile robot scenario where you have a mobile robot, a ground robot, and pedestrians. And it can work well there in that kind of a scenario. So yeah, so that's the answer. It can work with pedestrians, but pedestrians only so far. As for how it'll work in a mixed environment with vehicles and pedestrians, that's sort of tricky because by the time you sort of observe the trajectory of a vehicle, the pedestrian's already long gone. Uh, so yeah, so I'm not sure how it'll work with a mixed traffic scenario, but with a pedestrian only scenario, the vertex of centrality can be extended to that.
We have one question from the question and answer box. How does the current computation costs look like, considering there are going to be a lot of vehicles around the ego vehicle?
Uh, so in simulation, I've observed that the model works well for 100 vehicles. Um, After that, so what's happening is that at every time step, we're populating the graph one row and one column at a time, and it can work well for it works well for n is equals to 100 agents, but after that, there's a sort of lag, and while that lag is not of a concern from a simulation point of view, but if you want to deploy it in the real world, then you sort of need the delay to be uh, less than in the order of milliseconds or even less than that. So greater than n equals to 100 vehicles in the total simulation environment, that it works well. But after that, you need to reset the matrix to 0 and it starts again.
I think we have one more question on the chat.
Yes, the vertex centrality is so similar to summing the inverse of the distance from the. Yes, so that's the closeness centrality. So the closeness centrality definition is exactly that. You measure the reciprocal of the sums of the closest distance from the ego vehicle to every other vehicle in its neighborhood. The distance, the degree centrality definition is different. It sort of counts uh, the number of neighbors to you, but the closest centrality measures the inverse of the sum of all the distances of the ego vehicle to every other vehicle.
Okay, are there any more questions? We'll give a little bit more time.
Have you tried using the closeness centrality, observing just the vehicles in your ego core line of sight? Uh, so line of sight isn't the exact notion. So we assume that we have a location sensor like GPS, or we have a lidar, and we assume that it can sense the position. So that's the only assumption in our approach. We assume that we have the locations or the positions of all the agents in a neighborhood or a radius around the ego vehicle. So we assume a lidar that can rotate 360 degrees, and it can read the coordinates of all the vehicles inside a certain radius. So not just the vehicles in front of the ego vehicle, if that's what you mean by line of sight.
Okay, do we have any more questions? Okay, well, I guess since we have no more questions, we'll just end it here. Thank you again, Rohan, for doing this seminar with us. Everybody else, tune in next time. I think our next seminar is going to be in April sometime. So look to your emails to see when that next seminar is coming.
Thank you, Lena.
All right, everybody have a good weekend.